organizing this wonderful conference. And I will not thank the friends from yesterday for the drinking, so you can imagine my head this morning. Okay, so I will be talking about representation of solutions of nonlinear PDEs by branching diffusions. And this is a project which was started by Pierre-Henri Labordère. And as I will try to convince you, it's a beautiful idea that he came up with, and since then we try to exploit it in many directions. Pierre was motivated by nonlinear PDEs, nonlinear Black-Scholes equations, which are a consequence of taking into account funding problems. So CVA, KVA, we had an expose by, a talk by Stéphane yesterday about this. You naturally end up with nonlinear versions of Black-Scholes equation. And during the crisis, many people said, oh, it's finished for PDEs in finance, stochastic analysis in finance is finished. But in fact, we ended up with more interesting problems. Whatever linear PDEs became nonlinear. So we're still in business with that. Okay, so let me start by showing you the main idea. So it goes back to old work on the KPP equation, Kolmogorov, Petrovsky, and Piskunov equation. And then I will show you the basic argument. Why do we have this representation? And then go further and further to more general semi-linear parabolic PDEs, and then even beyond to hyperbolic PDEs and stochastic PDEs. So we'll see how much time you. I should stop by 11. Okay. Okay. This is the well-known result from the old days. So the KPP equation has this form. There is the heat operator, basically. If you think about an underlying stochastic process, this would be a diffusion with drift mu and volatility sigma. So double dot means the trace. So this could be also in D dimension. Doesn't matter. There's nothing special about the dimension. And then the nonlinearity in this equation is very specific. First, it's a power nonlinearity. It's a nonlinearity in terms of the value function, Vi. And the coefficients here, the Pi's, form a probability measure, sum of Pi equal 1. So very special. But as you will see, we can take away this condition very easily. These works were motivated by population dynamics, and therefore it ends up to these equations very naturally. So this will not be important that the PIs form a probability. So very specific nonlinearity. In terms of finance, it will fit to FVA problems. But if you have if you want to account for repo type of problems, then you need the nonlinearity in dV. Okay, so the representation is this one. We have to introduce particles which are labeled ZK, and the final condition G, which I forgot to write here. So V at time capital T is the final condition for this PDE, is equal to G. So as you see, the representation is multiplicative.
I'm sorry, just to fix idea, I is an integer. It could be anything.
This should be pk. K from 1 to n.
You
mean this one?
Yeah, is that
integers.
exponent?
Yeah, I from 1 to n. It has to be integer. Okay? Yes. That is important, as you will see. Okay, so you see it's a representative, it's a multiplicative representation, expected value of the products over all particles of this G of ZTK. And what are these particles? Let's see it on this graph. So you start from a parent particle, then you follow this diffusion with drift mu and volatility sigma, which you see in the equation here, the first part of the equation. And there's the beta here at an exponential random time with intensity beta, the particle dies out. And there is some particles, descendant particles, which are born at that date. And they will be labeled 1, 1, 1, 2, very natural type of labeling. Notations are awful in this talk, but very natural. You have to follow the logic, and then it becomes easy. So you see, if the parent particle is k, the next particle will be k1 or k2. You have to add one more. So k is a multi-integer. So this is the story about this branching tree. You have a diffusion which branches at some random time. Here it's an exponential with intensity beta, and it has either 2 or 1 descendant, because here I'm taking this particular nonlinearity. There's a v square or v here. Whenever it branches, the descendants evolve independently of each other and follow exactly the same dynamics. Drift mu, volatility sigma, one more branching time, which is relative to this particle. For this one, the branching time is here. It's independent. Everything is independent. And at every branching time, the new particles follow exactly the same dynamics. Drift mu, volatility sigma. So this is the nature of this representation. So at the end of the tree, you look at the particles which are at the extremes of the tree. So these are my particle k, in k capital T in this notation. Kt is all particle alive at time t. So you take the product over all particles which are alive at time capital T. You see, these ones are the alive at time capital T. This one is not alive. This one dies out here. So you just sum up over these final particles, and you multiply these g of ztk. So this is remarkable because from the Monte Carlo point of view, we have a nonlinear PDE, and we don't need to do this. If we think about probabilistic type of methods, we don't need to do repeated regressions, which are very time-consuming. So you see, we have a nonlinear PDE, and the representation is, if you think about Monte Carlo method, this is just you have to simulate this tree, and you average out this result, product of G of ZTK. So from Monte Carlo point of view, it's very convenient. It has other inconveniences, of course. You cannot win on all the tables. I will explain what you. Well, the first restriction is that the nonlinearity is very special. It has to be of the power type. Second restriction here, so far, there is no gradient nonlinearity, but this I will show you that we can do it. But one main restriction is that since there is a nonlinear, since the nonlinearity is in polynomial form, there is explosion of the solutions. Think of the Berger equation, for example. There is explosion of the solution. So we have to find ways to avoid this explosion, or to work with it to repeat this scheme, etc. And this is related to some work which has been done recently by Bruno Bouchard and Xiaolu Tan and Yi Zhu. Okay, so let me explain why this works, and at the same time have one first extension, which is give away the restriction that the PIs sum to 1. So I still keep some PIs, but I multiply by any function AI of T and X. So power nonlinearity of this form, and I also gave up on this beta minus V, which is an immediate change of variable, because I will need to get away from the exponential branching times. Okay, so how to have this representation for this type of equation? I will try to be clear. So notations are, for each particle, we have a duration of living, tau k. Each particle lives for a period tau k. And then what I call Tk is the accumulation of these tau k's. I will need to introduce this multinomial distribution, which takes the values I from 0 to n with probabilities p0 up to pn. So these are my ik. And again, I work with the diffusion with drift mu and volatility function sigma. Okay, so the idea is to start from this PDE and to treat the red nonlinear term as a source term. Forget that there is a v there. Let's take it as if it is a general function of t and x. If you think about this term as a function of t and x, then you have a representation of the solution in terms of the Feynman-Cach formula. So that's the starting point. Let's start from there. Okay, so this is what I want to show you, but let's go to the argument. I think it's important to understand what we're doing, and then let's see how we can extend it. So this is my Feynman-Cach representation. Again, we have this operator, which is generator of diffusion with drift mu and volatility sigma, and then this nonlinearity, which I put as a source term, so I have my Feynman-Cach representation with this source term. Okay. Now there are colors, the blue color and the red color, and I'm going to get rid of the summation and the integral by randomization, by introducing the randomization. So what is the randomization? For the blue part, I will multiply by rho, divide by rho. I'm not changing anything. And I'm introducing this rho bar. So rho is any density. Rho is a density, which is positive on the positive real line and integrates to 1. And what I call rho bar of t is the integral from t to infinity of rho. This is the notation. So we take this rho here, so I'm not doing anything, just multiplying by rho's and by rho bar and dividing by these terms. But now I'm going to treat this integral with respect to rho as an expectation of some random variable which is independent of everything. So that's the next step. You see, I'm introducing this tau 1. Tau 1 is a random variable which has distribution rho. So this plays the role of the exponential distribution from before. Okay? Another randomization that I have done in this line is the randomization of the summation. Instead of writing sum of pi blah, 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 I create this random variable I1. Remember, this I1 random variable is distributed as a multinomial distribution, taking values in 1, 0 to n with probabilities p0, pn. Independent, everything is independent, and then this is obvious, right? This equality is trivial. Just integrate partially with respect to the I1, you get this summation here. Integrate partially with respect to tau 1, you get this integral here. Okay? And similarly here, this rho bar of t, by definition, is the probability that tau 1 be greater than t. This is my definition. So this indicator function also is obvious. Okay? And now comes the now the problem is that this is not very helpful, because if you want to compute v at time 0, then this is not an explicit expression for v, because there is this nonlinearity v to the I. And we want to get rid of this v to the I. And the idea is to use the Markov property that whatever we have done here from starting from 0x, I can do it starting from this time tau 1, x tau 1, from this branching time. And therefore, if I start at tau 1 x tau 1, then I can write this as an expectation starting from this data of a random variable which depends on the next branching time that I call tau 2. Okay? So what is phi? Phi is the conditional expectation of whatever is inside this expected value conditional to tau 1. That's phi. Okay? So this is just using the Markov property. And again, we still have this power I1. We would like to get rid of this power. And the very easy idea is to write this expected value as a product of the same expected values. And now what we wish for is to factor out the condition expectation so as to get rid of it by the Tower property. Okay? And therefore avoid these regression methods. Okay, and the way to do that is to use is to observe that this expected value only depends on the distribution of whatever is inside. And therefore, I may choose independent random variables inside these expected values. And this is why we have these branching particles which are independent. If you use these branching particles out of any extension time, then you can factor out the expected value and get the product of the random variables, the expected value of the products. But you need this independence. And this is where the products come from. So this is the main idea. Main idea is to go from here to here by using independence. Okay? And now, as you see, once you get here, you throw out this expression inside, and by the Tower property, you get rid of this condition expectation. And you keep going. You keep going in the sense that in the phi here, you would have v at time tau 2 at the next branching time. V at time tau 2 to the power I2, and you want to get rid of it, then you are going to branch one more time, and the game is to send the number of branching to infinity. You want to send the number of branching to infinity until you eventually get away from capital T, and you're done. There is no nonlinearity anymore. So you push the nonlinearity further and further by these branching times. You want to get rid of this term. You see, this is indicator function of tau 1 less than capital T. By branching more and more, eventually this term will always be 0. So this is what you're targeting for. Okay? And so by doing this, you see that at any internal branching time of the tree, you get this A divided by rho. And at the extreme nodes of the tree, at the final nodes, you get G divided by rho bar. So, and this is why we have this representation, G divided by rho bar for the extremal nodes. And for the internal nodes of the tree, you have A divided by rho. So this explains this formula. Okay, so as I said, numerical implication, you can do Monte Carlo very cheaply somehow because you don't have these multiple regressions to do. But typically the result is that this holds true if capital T is small enough. I didn't put all the conditions here. We will have another result which contains the conditions. So the first extension that I want to talk about is to introduce a gradient term in this nonlinearity. So can we still do this for a more general nonlinearity, still of the power type? So sorry, this is too much complicated. Think of the case, this u multiplied by du, the Burger's equation. If you have Burger equation, u times du, can we still do this type of representation? Okay, so let's go back to our Feynman-Cach representation, remember? We create this rho, divide by rho, rho bar, divide by rho bar, and then randomize. So I'm just doing the Burger equation. Because as you have seen here, you can put whatever sum. We are going to randomize it and end up only with v to the random variable I1. Okay? So if I know how to do it for v dv, then I can do it for any summation of this type of terms. Okay, so to do this, let's act exactly as before. Now I have this nonlinearity here, and I want to push this nonlinearity as far as possible. But the problem here is that I don't have v squared, I have v dv. Well, we can handle this by using a trick which came from finance. This is which was used in finance, in fact, for Monte Carlo computation of the Greeks. So this v dv at time tau 1 x tau 1, exactly as before, I can write as an expected value at time tau 1 x tau 1 of this function phi at time tau 2, but then the dv is the derivative with respect to the space variable of the same expectation. And I think many people here are familiar with this Maliavin type of differentiation. You can differentiate this expected value by multiplying by the increment of Brownian motion divided by the difference of time steps. So here I'm taking sigma equals identity and mu equals 0 to make it simple. Well, this is very easy to understand. You don't need Maliavin in this context. This is just differentiating the density because the underlying process is a Brownian motion. So to see this, you know exactly what is the distribution of this xh. So you just write it as an integral with respect to the heat kernel, and then just integrate by parts, and you get this. That's obvious. Okay, so this is what we're using here, and once we get here, you see that now I can use again the trick of creating independent particles, branching, and then do exactly as before, except that I have this green weight which comes into the picture. And again, once you do this, you push the nonlinearity further and further by introducing new branchings. Okay, so you see we have the same figure as before.
When you do the integration by parts, the W does not perturb the integration by parts?
Okay, now we're going to talk about technicalities. Here, of course, there is a problem, technical problem that you have to solve because this, formally this is of the order of 1 over root of tau 2 minus tau 1, and that can be dangerous. Huh? Okay, there are some technicalities there. Okay, so we end up with a similar tree as the one before, diffusion, branching time, and then two descendants. Here I'm taking the Berger equation v dv, two descendants at each point in time, one descendant of type 0, one descendant of type 1. I'm using the colors, and then each descendant has an independent life, and the type 1 descendant is the guy who gets differentiated. He gets a weight delta w divided by delta t. So it's exactly the same type of representation, except that whenever you have a derivative, you have to multiply by this weight. So because of that, we end up with a formula which looks very much like before. Where is the formula? There, yes, this one. So this is 1 over rho bar times the final value g. Forget about this guy. I don't want to talk about it. You have to put it to have integrability. And then you have 1 over rho of the difference of branching times, and this is the b which is in front of the nonlinearity, and this is the weight for the differentiation, which depends on the type of the particle, wk, and then you say wk is either 1 if the particle is not differentiated, or delta w, delta t if it gets differentiated. So exactly the same type of representation, and exactly expected value of psi can be computed very easily by Monte Carlo. You just have to simulate one tree. There is no regression again. But we can avoid these regressions. And here I have put the conditions. So I'm not expecting that in this very short period of time you can understand what is the origin of these terms. But I just want to insist on something. The condition is of the type capital T less than something. And this is expected in this type of problem because this is Berger's equation, there is explosion. And in any equation of this type, it will be available for a short time. This will hold for a short time. And we need P equal 2, by the way, if we want to have a central limit theorem and to apply this method for high dimensional problems. Okay, so the main problem here, the main technical problem, is to take care of the integrability, and namely of this d delta w delta t, which is of the order of 1 over root delta t. And you see that if you want L2, 1 over root delta t, if you square it, this becomes 1 over delta t. It's even worse, not integrable at 0. So this is why we have to choose the density rho has to be chosen so as to have the required integrability. So all the technicality is in the passes to the limits, how to push this branching further and further until you hit capital T. Okay, one numerical example before going further. The numerical example is a Berger equation in dimension 40. Well, it works very well. As you can see here, the true value is the blue one. This is the true value. And what we get by running this just naive Monte Carlo, this is just 1 over t, sum off. 1 over n, number of simulations, sum off. We get very nice convergence with standard deviation, which is decreasing as wished. So you may ask, how can I have an explicit solution of the Berger equation in dimension 40? Well, the trick is to adjust this B0, which is a function of Tx. I choose my favorite solution, which I'm taking here to be bounded as smooth as I want. I take this u of Tx, I plug it into the Berger operator, and I put the B0, which is the result, so I create a solution. So with this, we see that it works. But again, it works for small t. This is a local result. To make it, to avoid this small t, again, there is a work by Bruno Bouchard, Xiaolutan, and Nizar, which shows that you can redo the simulation t by t. In fact, locally, you can put them together, but then it becomes more complex numerically. But it can be done. It becomes not as simple as just a branching tree and take Monte Carlo. Okay, next extension that I want to show you. Oh, the problem with, if I had a fully nonlinear parabolic PDE, then this Maliavin automatic differentiation or likelihood ratio still works, but then the weight becomes delta w squared minus delta t divided by delta t squared, and this is already of the order of 1 over delta t. So this is still open. We don't know how to prove the convergence with this one, because now the singularity is wider. Okay, next extension is, let's get away from these parabolic problems. There is an extension to the elliptic case, which will be presented by Julien. This is more difficult because you have to take care of the boundary, which is not easy for the Maliavin differentiation. So Julien will talk about that. I will be talking about initial value problems. Think of wave equation. So let's get away from the word of diffusions. And in fact, we were very surprised to realize that the method works even for this type of equation. So very general initial value problems. You have capital N time derivatives. So for the wave equation, you would have second derivative with respect to time here. And then you have these are space derivative. D alpha u is this derivative, alpha 1 derivative with respect to the x1, etc., until alpha d derivative with respect to xt. So any space derivatives, you have many examples in physics of these equations. Wave equation, as I said, this is Airy equation, comes with 3 derivatives here. The beam equation comes with 4 derivatives, and second 2 derivatives in time. Schrödinger equation can be dealt with also. Everything I will be talking about, you can do it for complex coefficients. You just treat the real part and the imaginary part separately. And the nonlinearities in Schrödinger equation, this is focalizing and defocalizing effects. So don't ask me about details about this. We just try to find examples. So you take any equation like this, and the basic theory of partial differential equations says that if you have capital N derivatives in time, like this, then you need capital N boundary conditions at 0. And these are derivatives with respect to t. Okay, so for these equations, our method still works. And the idea is that for all of these equations, you have a linear representation of the solution. For those who have done basic course in PDEs, the way to do it is to pass to Fourier transform with respect to the space variable. And by doing Fourier transform, because the coefficients are constant, you can report the derivatives, space derivative on the coefficients. So this is just integration by parts. And then you end up with an ODE, only an ODE for the Fourier transformed functions, parameterized by the Fourier frequency. And by doing that, you get this linear representation of the solution. Well, the theory says that you have a linear space of solution, blah, blah, blah. Everything is linear, okay? So we will introduce nonlinearity by replacing f here by nonlinear terms in u and du, as before. But so far, this is linear. And the main idea is to observe that this is nothing but a replacement of the Feynman-Kac formula. For the heat equation, you only have one time derivative. So capital N equals 1. Gn is the heat kernel. And this is exactly Feynman-Kac expressed because you know the heat kernel is explicit, so you can write everything as an integral with respect to heat kernel. Okay? So this is exactly a replacement of the Feynman-Kac representation. And, well, the Gn here you can obtain through its Fourier transform. So Gn is the Fourier inverse of G hat n, the G hat n being the exponential of this matrix. So everything is explicit somehow. If you want to capture more examples, you have to work under assumptions where these functions are not in L1. Otherwise, you lose many examples. So we work with distributions. We take all this in the sense of Schwarz space, and these are all distributions. Okay, so now the idea is to do exactly what we have done with the heat equation. This Gn's here, now we have capital N Gn's. This Gn, in contrast with the heat equation, have no reason to be positive, have no reason to be integrate to 1. Okay? If you run the examples from before, then you can see that for the wave equation, Gn are positive, but do not integrate to 1. But for other examples, Gn can have any sign. For the Schrödinger equation, Gn will be complex, of course. Okay, doesn't matter. The idea is to, well, we will assume that Gn has total mass, which is finite, and then normalize this Gn and take away its sign. Okay, by doing this, you see what we're doing is we are taking multiply by the sign, divide by the sign. It becomes positive, and then normalize. And then we create a probability density function. So create a probability density function, but then you have to carry the total mass and the sign. This is what we get in this representation. Utx is this multiplication of the boundary conditions, little f, and the source term, capital F. Gamma is what? Gamma is sign times total mass. This is exactly what I need to introduce this randomness. And now the random variables, the I is as before, this multinomial random variable. The rho is as before. Tau has density rho, exactly as before. And the new thing is that I'm creating these particles with this distribution. So absolute value of these green functions, Gn, normalized by the total mass. Okay? Now, once you have this representation, this is exactly the replacement of Feynman-Kac representation. And now I can introduce nonlinearities here. So if we introduce nonlinearities as in the KPP equation, then you have exactly the same type of representations, except that you have to carry again the total mass and the sign. This is the gamma. The only difference with the previous formulas is you have an adjustment with the mass, total mass and the sign. You can also deal with the case where you have nonlinearities in u and du, and again you have the same type of representation, and you have the same kind of observation for this differentiation, automatic differentiation, because after all, the representation, the linear representation is a convolution with respect to these functions gn. So if you want to differentiate, you can differentiate directly the kernel. This is exactly what happens with this Maria-Van differentiation, differentiating the density. So there is a perfect substitute for the method that I showed you in the semi-linear case. And so these are numerical experiments for the nonlinear wave equation. So again, two derivatives in time, two derivatives in space, and this nonlinearity, dimension 1, dimension 2, dimension 3. In green, you have the solution of the linear equation, so without u3 and u2. In red, you have the exact solution. Again, we know what is the explicit solution of this equation for the same reason as before. And what we get by Monte Carlo are the blue points, and you see that we can match them almost perfectly, yeah? Because we're taking many paths here, of course. Okay, dimension 2, it is also working. Dimension 3, it's also working. I'm not familiar with numerical analysis, but I think it can be hard for them to do dimension 3. I have to talk more to people doing wave equation. So this might be interesting for them. Another numerical example, again in this family, but now with nonlinearity in the gradient. So this comes from also an equation in physics, but simplified to get this form. And again, it's working. This is in green, again, solution without nonlinearity. Red is the explicit solution, and you see that we match this explicit solution. Okay, the final extension that I want to show you is the stochastic partial differential equations case. So here I'm back to the parabolic operator, but I'm adding a noise which is a Brownian motion. It's not a space-time noise. And this is a work in progress. So we have decided to start with this equation. And well, now you can do as before. You can feel, okay, I have a beta here minus u. This means I have an exponential extinction time of the particle. And when the particle dies out, two particles are born, because this is u squared, and continue as before. But the source term now is this w dot. And w dot, from the Monte Carlo point of view, is not well defined. So the first step is to get rid of this w dot. And to get rid of this w dot, you do something very natural. You take the solution of the equation without the nonlinearity, without the red term, you see. This is exactly the same equation, except that it doesn't have the red term, the red nonlinearity. Then for this equation, you know the explicit solution. This is the explicit solution. And then you just subtract it to u, and you get, now instead of a stochastic PDE, you get a PDE, a parabolic PDE with random coefficients, random media. Okay? And now for this one, we can apply the methods. For this one, we can apply the methods, and we get the same type of representations. I'm saying under convenient conditions. I should say under conditions which has not been written yet. So we are doing this calculation. But, well, the point is that we have the random variable that needs to be taken, which pops up naturally with this method, but we have to make sure that it's integrable, etc., etc. So again, we have the same type of representation, product over particles living at time capital T of G or WTK, product of internal over internal particles with this random function u0. This is random function u0. So this expectation is conditional to the randomness of u 0 to the Brownian. This is why there is an omega here. Okay. So this is the end of my talk. Again, this is not finished yet. Okay, I'll stop here. Thank you very much.